Well, hello. Welcome to another DevNation Live. I'm actually here in Milwaukee hanging out with a group of people talking about Istio. And it turns out we're in the central time zone. I didn't realize that until just a moment ago. But we are live and we're ready to rock now. And the good news is we're here to talk about Kubernetes patterns specifically today. We have Roland Haas here, who's coming to us from Europe, and he is our resident expert on all things Kubernetes. He's been giving this talk now all around the globe, and it actually is a very exciting topic. I'm certainly very excited about Kubernetes. I know the folks here in the room are excited about Kubernetes and Istio in particular. So we do have a live audience here with us, but we have several hundred of you on the line. It looks like almost 600 people right now are on the line, so we want to make sure that we get your information. Or we get your questions in the chat tab. So keep that in mind. I'll be trying to answer questions in the chat tab in real time, but we'll also collect questions for Roland at the end. So he'll kind of be doing his presentation, and then we'll ask him some questions verbally as we get towards the end of our session. All right, so hopefully you guys are ready to go. Roland, it's over to you now.
Yeah, thank you very much. Thank you for the introduction. Welcome, everybody. It's really awesome that so many people are joining here for some Kubernetes goodness. So let's get started. Okay, so this talk is about Kubernetes patterns. And of course, before we start into the concrete patterns, let me give a brief overview of Kubernetes itself, what Kubernetes is. So in case you do not know about Kubernetes, it's an open source container orchestration system or platform, which has been open sourced by Google 4 years ago. And actually, it's all about orchestration of containers or Docker containers mostly. And an orchestration system is about scheduling, which means that you want to distribute your containers over a whole fleet of nodes. That is one of the most important tasks of such an orchestration platform. And another high-level feature is that Kubernetes provides horizontal scaling, which means that you can have many copies of your application running on different nodes. And also Kubernetes is responsible for scaling up and down, and it also has a way to do auto-scaling. So to use some kind of metrics to find out how many pods are really needed. A very important characteristics of Kubernetes is that it's self-healing. This is due to the fact that Kubernetes itself is a declarative resource-centric platform, which means, what does it mean? So it means that you do declare a kind of a target state. So you declare the state which you want to have of your application. So how many copies you should be running, where's the image for your application. You declare this, you hand this over to Kubernetes, and Kubernetes actually then checks what is the current state and compares it against this target state. And if the current state and the target state differ, then Kubernetes does a reconciliation to get to the target state. So there are some controllers running in the background, and they're constantly monitoring the system and try to get to the target state. And if you want to change something, you just change the target state. That's how Kubernetes works internally. And everything is about these kind of declarative objects, also called the so-called resource objects. Another nice feature of Kubernetes is service discovery. You know that we all live in a kind of a microservice world. So we have a lot of different services which depend on each other. And of course, these services need to find also each other's, and Kubernetes helps here. Kubernetes does this by using DNS, the domain name service. So you just look up another microservice by its name, and everything is performed by Kubernetes. So Kubernetes manages this DNS server. And then one of the last high-level feature I want to present here is about installation, updates, and rollouts and rollbacks. So Kubernetes helps you to get your applications out to the cluster. It also helps you to make updates. It knows very different update strategies, as we will see in a minute. And this, again, is all done declaratively, which is very, very nice. And if you access the Kubernetes cluster, there's a central API server, which exposes a resource-centric REST API, which means you have very standard CRUD operations, which is about creating, retrieving, updating, and deleting these resource objects. And then it's that, that is everything is declarative. So you have resource objects. They have a certain kind of type. We will see some examples in a second. So let's go to the next part. So actually, this is really a high-level Kubernetes introduction. We will see much more in the next slides then. But before we come to this, I want to just explain shortly what I mean with design patterns. What are patterns? So a pattern actually is a kind of a repeatable solution for a software engineering problem in our case. Repeatable means that it's not really a very concrete solution for a concrete problem, but a solution for a whole problem class. So you can really use this kind of pattern in different circumstances, in different contexts. And this is where patterns come from. And yeah, let's have a quick look into the history of patterns. So there was a very famous book written in 1979. It's about a pattern language from Christopher Alexander and his co-workers. And actually, this is not about software. It's really about architecture, which is very interesting. And you find several hundreds of patterns there, which differ in granularity. So there are patterns like cross-country fingers, which describe how you should design whole cities, but also very fine granular patterns. Like, for example, one pattern is called different ceiling heights, which means that you should architect your house in such a way that the rooms have different ceiling heights, so it gets more interesting. And these patterns, everything have some name, they're interconnected, and they build some sort of a language, which is quite nice because with this language, you can easily have a common ground where you can continue on. And this kind of idea swapped over then in the 90s to this very famous book. I guess everybody of you already have heard about it or even read it, maybe. It's about called Design Patterns from the Gang of Four. And it's, there are patterns like singleton, like a factory, like a delegate. And if I tell to you what's about a singleton, then you already know what this means. So we do not have to explain the concept behind this. So we have all on the common ground. So this is the nice thing about patterns. And then there have been many other books about patterns, about enterprise application integration patterns, and also more specific topics like for Kubernetes itself. So actually by accident, my colleague Biljam has started a book about Kubernetes patterns, and I'm co-authoring here. And what I'm going to present you now in the next, the remaining 20 minutes or so are really patterns out of this book. Of course, this book holds many more patterns, which I cannot explain here because of the lack of time. And the interesting thing is that Kubernetes itself, it's an application, it's a platform, it's a orchestration platform, as already mentioned, and it already provides a lot of patterns out of the box, so implementation of patterns. So it's some kind of the core features of Kubernetes itself are patterns. They are the collected experiences from Google, so the book is a little bit not so only about patterns which are on top of Kubernetes, but also describes the patterns which are inherent to Kubernetes itself. Okay, so this is about the intro. Now let's get started. So first of all, every pattern I'm going to show you have a very simplistic structure. So for the sake of this presentation, so first of all, I will give you some kind of the problem, describe it, the problem, which is going to be solved by the pattern. Then, and each pattern has then a name and a solution for that one. And if you're interested in this kind of theory behind patterns, there's a very, very interesting article written by Martin Fowler. And there are different formats about patterns. And I can highly recommend this article if you just want to know more about history of patterns and how patterns can be written there. Okay, but now really let's get started. So first of all, let's talk about the foundational patterns. And as I mentioned, these are really about the core concepts of Kubernetes itself. And this pattern is all around about how you can create and manage applications with Kubernetes, and it's called automatically unit. And this unit is actually exactly these kind of resource objects I have mentioned in the beginning. The most important of these resource objects is a pod, and this is the atomic unit of Kubernetes, and it's a collection of one or more containers actually. Then on top of this, there are services which are the entry points to these pods, so how you can reach them via the network. And another very important concept of Kubernetes is around metadata of all of these objects. So every object can carry labels and annotations as metadata. And you can group these resource objects also into namespaces to separate them. So how does such a pod look like? As I mentioned, a pod is an atom. It actually gets an IP address. So everything in Kubernetes is running on an internal network, which is hidden from the outside. So typically you cannot reach this internal network easily. Then, as mentioned, pods can carry labels, which is very important, as you will see in a second. And then you have containers running within this pod. So actually, it's a collection of containers that you typically, or mostly, you have pods with one container also, but there are certain situations and where you are using multiple containers within a pod, and all of these pods are sharing certain characteristics, namely, especially the network space. So every every container within this pod can reach the other container via localhost and over a port. And of course, they have to share all of the ports there. And they can share also files data via volumes. So this is not done automatically, but you can configure such a pod to share file data here. A very important aspect here is that such a pod has an ephemeral IP address, which means when the pod dies because of some outage or for any reason, and it comes back again, then it typically gets a different IP address. This is important. So this IP address is not stable. So you typically, or you never access a pod directly with this IP address. You need a kind of an abstraction over it, as we see in a second. But before we come to the so-called service, which is actually the abstraction over the pod for reaching it, there's another concept which is very important, which is the so-called replication controller, replica set, which I'll show you in a second. Before that, I have this slide here, which shows you how such a pod declaration looks like. So you have here a structure which is common to every resource object in Kubernetes. In that case, you have a kind, you see there on the top. You have a section called metadata. So sorry, there's some fault in the indentation. So actually, this YAML file has then several sections like metadata and a spec section, which is important. And you see this in every resource object there. And the spec section then has a list of containers, and they have an image name, which references a Docker image. They have a real name. You can expose ports from a container, and as I said, you can have multiple of these containers. So this is a very simple declaration of a pod. In the real life or in the wild, you will see much more complicated versions of this declaration. Okay, but now to the next part, namely to the replica set, because such a pod is just running, and if it dies, then it's gone. Yeah, but I said one of the characteristics of Kubernetes is the self-healing, which means that a pod gets recreated if it dies. And you need some kind of entity which is responsible for this. And this is exactly what a replica set is for. It's really responsible for managing pods. And very important number here are the number of replicas. And the number of replicas simply states the number of copies of your pod which should be kept. A replica set also holds a template for creating new pods. So actually such a pod declaration, which we have seen in the slide before, is embedded in a replica set declaration, so that a replica set controller which has to create a new pod knows how to do so. And then finally, you have a label selector for choosing pods, which is important so that the replica set controller really can find out how many pods are really running and compares that to the declared number of replicas. And if there are less numbers than replicas, then it just creates a new pod. Otherwise, it just kills one. Okay. Here you see an example how this replica set looks like. So you have the selector, you have the pods here, and actually we have specified we want to have 3 replicas, we have 3 pods, and that's fine, everything. And you see the selector and also the name labels which are attached to each pod. Okay, the final resource which I want to show you here is that the service, which is again, as I mentioned, the entry parent for a set of pods. So you can, again, the pods which are behind the service are chosen by a label. Interesting is that this service has a permanent IP address, so it's kind of a virtual concept which doesn't go away. So a service is always running. It's no life cycle in that sense. And actually, if you access a service over his IP address, it makes a kind of a mini load balancing back to the pods and does some kind of round robin distribution to the pods. Yeah, that's mainly is. And if still you have an internal IP address, and if you want now to expose this service to the outside of the Kubernetes cluster, you need then another object, which is then a so-called ingress object. And there you have an external load balancer, which picks it up and delegates the external requests to the services. Okay, this is again, it's only a brief overview of the core concepts. So there So you have to go back one slide. So there are many more of these objects. You see here that the pod here is in the center, but you have many objects and which are managed by Kubernetes. But the way how you manage them is always the same. So you have this kind of unit, this automatable unit. You can give it over to the API, and then Kubernetes takes care about this. Okay, now let's switch to the next pattern. And this is all about how you can deploy your applications and how you can update them. And how, obviously, how this works with Kubernetes. And you have to distinguish between a declarative versus imperative deployment. What I want to talk about is a declarative one, where you say, again, you just specify your target state and how you want to have an update to be done. A deployment is, again, other resource object from Kubernetes. It holds, again, a template of a pod. But if a deployment starts, it does not create the pod. It just creates a replica set on the fly, so that it manages multiple replica sets. So one replica set for each version, for the old version and for the new version. And so it can also do an easy rollback to the old version by just activating the old replica set. As we have seen, a replica set holds the number of replicas, and the deployment just varies these number just to ensure that the old version gets scaled down and the other one gets scaled up. It knows about different strategies, update strategies out of the box. You can declare it simply as a simple field. And what's also interesting about this deployment is a side note. So deployment is a resource object which has been inspired by OpenShift. So in case you don't know OpenShift, OpenShift is an enterprise distribution of Kubernetes made by Red Hat. And actually it's Kubernetes in its core, but adds some extra features on top of it. And the deployment, which I'm describing here now, was really one of the first features of OpenShift, which was not present in Kubernetes at the time. But then it was so successful, a deployment company within OpenShift, that the whole community decided also to implement a similar concept within Kubernetes. And it's a good example how this kind of interaction between the communities, OpenShift communities and Kubernetes communities, are really interwoven and really exchange ideas in both directions. Okay, now let's have a look at the different update strategies. So the first one is a so-called rolling update. And the good thing about a rolling update is that you can realize a zero downtime update. So you can realize that your service never gets down. And how does it work? So actually, as mentioned, you have a deployment and you have a replica set. This is the blue one at the top, represents the old version, 1.0. And then you specify the new version, and the deployment just does scale down one by one, scale down from the old version and scale up from the new version, and this one by one. So it scales down one container from the old version and scales up the new one, so that at any time one of the containers, either one from the old version or for the new version, is running, and the service actually just does a dispatching to both of them. This works perfectly fine for stateless applications, of course, but for sure, if you have some kind of a database behind and your update needs some kind of a schema update on the database itself, then you have to ensure that both versions can work at the same time on the same database schema, which is possible. So you have to help here as application developer. You have to make this kind of support for allowing both versions to run on the same database schema. So it's not for free, a rolling update. Just want to mention that one. The other one, the alternative for a rolling update, is a fixed update, where you just say, okay, I'm just tearing down all of my old versions, then switch off the service and fire up the new ones. And of course, in this case, you have some kind of a downtime, but you can in the time in between before you scale up the new version, you can of course make any schema update you want to. Let's go on, and then there's some kind of variations, like a canary deployment, and this is actually it's not directly supported by Kubernetes as a concrete deployment strategy, but you can easily do it on your own by just using two different deployments. And here in this case, you permanently just scale up one of the services and scale down maybe one of the old services and run them both in parallel. And then you can, of course, check whether your new service works as you like. You can test some kind of new features, canaries. And if you don't like it, you can scale back the old application to its full blast and throw away the new version. Of course, the same applies like for the rolling update, that both versions need to be able to run on the same database scheme. And then finally, we have a blue-green deployment, which is a little bit a mixture between rolling and update and the fixed update. So here in that case, you run both versions in parallel. Actually, your new version even could run to a different database if you like to, and you can test everything on this new version, whether it works like you want to, and then do just an atomic switch from the old version to the new version. So you cut off the service so that it does not delegate back to the old application anymore, but just to the new one. And this can be done in kind of atomic fashion. The drawback here is, of course, that for a certain amount of time, you need to have twice the capacity for your application. So you need, in that case, you have 6 containers running instead of 3. And here's a nice picture drawn by Belgium itself. And this really nicely graphically demonstrated several strategies which you can choose from. So you see here the rolling update, the recreate deployment, and blue-green releases. You see that you need twice the capacity. And then typically this means also twice the cost for this time, and also the canary run. Okay, that's about the deployment part. Now let's move on to a next category of patterns, which is about the structural patterns. Let's have the first one, and this is all about the problem how you can initialize your applications, actually. And therefore, there's a so-called init container or initializer. And this init container is also part of a pod, which means it's also a container you declare it again in your pod manifest. And this is a one-shot action which happens before your pod starts. So it's a container which also finishes after a certain time. And only when this pod has been finished, then the real application containers are started. Important characteristic of these init containers should be that they're idempotent, because your pod can go down anytime and can go up, go back again, so that you can run the init containers multiple times without any side effects. And important also is that the init container has its own resource requirements, so you can declare how many memory and CPU such an init container requires. It's the same like for the application containers, which we describe in yet another pattern, which is called predictable demands. But unfortunately, there's not much time to show that one. But here you see also in this graphics how this works. So first of all, you can have multiple init containers. So you run one init container after each other. The init containers are really good, for example, for doing some kind of pre-processing, like initializing configuration and so on, or initializing a database schema, something like that. And when the last init container has been finished successful, then all the app containers are starting in parallel up. So this is the init container. And you see it in many situations. Init containers are very, very useful and a very common practice to use for initializing your applications. Okay, then let's go on to the next pattern, which is probably one of the most famous patterns in Kubernetes. This is a sidecar. And the idea about the sidecar is really, or the problem which this pattern solves is, how can I extend the functionality of an existing container? And it's about runtime collaboration of containers. As we have seen, a pod is a perfect vehicle for realizing such a sidecar, because all the containers within a pod, they are sharing networks and volumes. And so you can do something like this, that you have here 2 containers running in a pod. So you have a main container, which is a plain HTTP server or Node.js server, which actually serves just data from the disk. And this is just static data. So this main container doesn't know anything about updates of the data which it serves, but you can easily stick a sidecar into this main container, which does a periodical check on some kind of a Git repository on the outside and updates the local data on the disk. And so you can add a new functionality to your whole application, namely a periodical update of your data which you want to serve, without changing the main container itself. This is very easy, because there you can make some compose stuff and create more complex applications out of simple containers. And in the book, we have also a very easy example how you can do this really easily on your own. This very example is given in the book, if you're more interested there. Then we have some kind of specializations of containers. One of is the so-called ambassador, which is just a way how you can decouple the access to the outside world for a container. So it's also known as a kind of a proxy. And typically infrastructure services like circuit breakers or tracing, or even so many of the service mesh out there also are realizing their infrastructure services via an ambassador or a proxy. And this works like that your container, your application container, just does not connect directly to the dependent service it wants to reach out, but just on a port and local host. And then you have a sidecar container which is listening on this host and acts as a kind of a proxy to the outside. In this example, it's just a cache which is added to a database access. The opposite of an ambassador is the adapter. And this is simply how you can decouple access to a container from the outside world, which means that you can provide a uniform access to your application. A good example here is monitoring. So for monitoring, you can, let's assume that you have a monitoring system like Prometheus, and Prometheus just expects your monitoring data in a certain format, but not all your applications that you can deliver this format. But at the end, you just add an adapter in here, which transforms the proprietary format to the expected data for Prometheus. This is also a very nice thing, and you will see this also quite often. Okay, let's go quickly to the advanced patterns. We are, which is then even a step further. And here it's the idea is how can I extend the platform itself without changing it? And there the idea of a custom controller comes in. And this custom controller works quite, it's a entity which is running in the background. It's a service running in the background, and it registers for certain Kubernetes events. And if any of the resources changes or over the API, so if something happens there, then these controllers get notified, and they can react on these changes and perform certain stuff, like, for example, this kind of reconciliation. This works like that. As I mentioned, they are listening to the API that makes the state reconciliation, and to make the current state like the declared state. And they're often used together with custom resources, which is one kind of the next pattern. But it's tend to be that there are two kind of categories of controllers. There's one of a simple extension controller, which really extends Kubernetes about new features. But there are more and more kind of application controllers, which really brings kind of business logic with controllers into Kubernetes and combine Kubernetes with an application-specific domain, which is very interesting. And this is something which is currently emerging more and more as a pattern. Let's talk briefly about the custom resources. So custom resources about custom resource definitions, which are managed by Kubernetes. They can be, so you can create your own types of data. You can access them via the Kubernetes API as any other resource, and can then use a custom controller. So this is, it looks like here you just define it, you have a type custom resource definition, and there you just define the name here. In that case, you have a Prometheus kind of option. So after you have registered this CRD, then you can use really a new object with a kind of Prometheus in that case. And of course, to make sense of this Prometheus resource, then you have a controller running in the background which just reacts on this custom resource Prometheus. Here's an example how such a custom resource actually could look like. And you probably guessed it, so this resource really is used for installing Prometheus in your cluster. So if you want a Prometheus server, you just install the controller, issue such a resource, and then you are done. Okay, so the final slide here is brief about operators, because this is also some kind of a pattern which has been emerged, and it's actually not much more than a combination of a custom controller and a custom resource, so it's just another synonym for them. And actually, there's currently a very nice framework by CoreOS, which provides an operator SDK for creating your own operators. So you can just use this. It's a Go-based SDK, so if you want to write your operators in Golang, then this is where the place to look for. It has a lifecycle manager, which allows your operators to be updated, like applications, and to be managed. And then there's also metering, which is about monitoring the usage of your operators. Okay, here's the final picture. As I mentioned, you have a whole scale of controllers. You have easy controllers, which even work without any custom resource. But you can have also much more sophisticated controllers, like operators. Or you can go even so far that you, for example, have a resource which describes maybe kind of a Kafka topic, and then just deploy this topic, and then you have some kind of messaging already in place. The same for enterprise application integration. You deploy integration custom resource, and then you have some kind of camel runtime created automatically. So these are the ideas which emerge more and more. Okay, so I think we are at the end now. So actually, I could only give a very brief overview of some of the patterns. You find many, many more of them in this book, if you like. There's also a free white paper from Reddit, which you can download, which also have a summary of these patterns. This will be the link to these slides will be in the published version of this slide deck. And then there are, of course, there are also many, many free books, awesome books written by Reddit. Also have the slide then in the published slides. So it's about like Istio service meshes. You can get all sorts of various aspects of Kubernetes. So probably Burke can tell more of it. So yeah, so that's all I have for now. So
all right. Well, you wouldn't believe the volume of questions we have had in the chat tab over here, the Kubernetes tab. It's been about 1 million of them, and I tried to answer as many as possible. Do you have any specific personal advice or interest in how to run a database on a Kubernetes cluster or OpenShift cluster? Do you have any specific patterns there that you think are appropriate? That came up a lot, running my database, dealing with my storage.
Yeah, actually, I think this is one of really the very interesting topics is about stateful applications, so like a database. And actually, I have not really a concrete recommendations. Actually, there are two camps. Actually, one of say, okay, we run the database outside of the cluster and just access the database from there. But more and more people really want to have everything within the cluster. And then there are, of course, specializations for databases like for Postgres and other add-ons, which allows you to run such stateful applications within the cluster. And there's even a resource, a stateful set, which allows you to configure this one. But actually, I have not really a concrete recommendation here.
Okay. And then there was a neat question related to, you mentioned controllers and the use of CRDs and the concept of extending the platform APIs with that. Could you expand on that a little bit more? Because I think that was a point of confusion for some folks. Yeah. Like, what do you do with that?
Yeah,
what's the primary use case?
Yeah, actually, one good example is that you have some kind of custom resource for describing another application you want to install, like Prometheus or like HT database. But another example would be for such a custom controller is that you might want to expose a port with an ingress object. So actually, you have seen this kind of services, and you could imagine that you can put a kind of metadata on the service, like expose to, and then you could have a custom controller running in the background which just checks every service for this label. And if this happens, it creates some kind of an route or ingress object on the fly to expose this service. And actually, there are certain controllers like this. Another example of such a custom controller, how what you could extend is to have a label on a config map which points to an application. And then every time a config map, which is an abstraction of a configuration file, changes, then you could have a controller which restarts your application. So you can kind of a hot reloading, typically just by adding this kind of new controller. So these are the simple controllers, how you can extend the functionality of the platform, even without custom resources.
Okay. And we're actually out of time, unfortunately. We're supposed to keep these to 30 minutes. And I appreciate that we have had a lot of people today. We had, I think, 700-800 people that showed up. The last question that I'll make a point of, there is someone who was talking about resource issues associated with worker nodes and JVM-based workloads, Java workloads. Mm-hmm. And so I know you know this, Roland, and I added a link to my Java Docker fail presentation. So just look for Java Docker fail on Google. There's a blog post on this. I have a whole presentation on Google. Yes, by default, the JVM will eat all your resources and blow things up. So that's covered in the intro class that we have. Roland, do you have any comments on that?
Yeah, one comment is that if you have the chance to switch to Java 11, then you should do, because now it's much more aware of containerized environment for the new Java version, which has come out, I think, 1 week ago. And actually, yeah, if you're running Java 8 in the container, you should really be very careful and check out Burr's presentation or the recommendation there, where you really should set the maximum memory to your JVM when you start them, and that you should really put your Java JVM into a kind of a cage yourself. Otherwise, you will blow up your containers for sure.
Yeah, and Roland has some nice scripts in his base images that he supports that deal with that specifically, right? The that go out in there and look at the C group settings to ensure that their JVM doesn't blow up. So it is tricky, but it's very solvable once you learn the trick. Awesome.
Yeah, for sure. Yeah.
So much.
Yeah.
All right. Thank you
very
all.
much,
Have a great.
everyone. Thanks. Bye-bye.